Welcome back, everyone, after lunch. Hope you enjoyed your lunch. It was a nice long break. So it's my pleasure to introduce Rainer Goebel. Rainer is a professor and director of the Neuroimaging Center in Maastricht in the Department of Cognitive Science and Psychology. He is, again, one of the pioneers of the field, in amongst the too many contributions to the field that is produced over the years. He is the creator of BrainVoyager, which is one of the most commonly used software. And so we have the fortune of hearing how BrainVoyager works exactly from the father of the. So thank you so much for coming all the way from Maastricht to this talk. It's a great honor to be here, and we look forward to you. Thank you so much, Renzo.
Thanks so much, Luca. Thanks so much, Renzo. It's a really pleasure to be here. And I want to present a bit topics we have already wonderfully presented with John and from Renzo, but a bit from the perspective of BrainVoyager. And it prepares also a bit for the exercises to move. So we have heard a lot that what we are interested in is the mesoscale, right? So it's the level where we can learn from the organization of the brain in maybe the sub-millimeter space. Because there we might be able to learn about principles of coding, especially if we consider the columnar aspect of mesoscale, but also about, as you nicely have heard, feedback and feed-forward, and maybe we can separate that, which is important for many cognitive questions, and especially for higher cognitive functions. The problem I'm having when starting to develop the tools was that I'm not interested in averaging at all. So when layer smoothing came out from you, John, I basically implemented once, but I never used it for any publication. And the reason is that I'm usually interested, it's my passion to understand columns and their depths, and the neighboring columns do not the same thing. What you said earlier is exactly not what happens, because if you want to disentangle the column for left motion versus right motion or so, then you need to not smooth the layers because you remove your effect. So that's the level where I'm interested in, and many of the work is really at the level of small cortical patches. Nonetheless, I will present BrainVoyager in a mixed way, how you can analyze the data of layers, more or less in a similar way as if you have whole brain data, but I show the particular problems and what they do something different in this talk. I will show you this mainly via the interactive graphical user interface of BrainVoyager, which I show not much here, but a bit so to prime you for tomorrow, for the hands-on. And there I'm working currently on a tutorial. It will not be fully ready tomorrow, but it will evolve in the next days or weeks, and then hopefully can be also used for self-study for others, because I like the dataset very much and hope that people can learn this also then with a tutorial. I will skip that. We heard a lot about this, another sketch of this. I want to start with some central questions. One which backed me when I started already about 20 years ago to want to have Camille 7T to do layers and columns. Basically at that time, and is still valid today, the central question also heard about earlier is, do my anatomical voxels match my functional voxels? And that has to do, as we heard, not only with co-registration, but also with motion within runs and across runs. And if we want to have separating layers or columns, and we might be able that one volume of functional data, it matches, but if then, your data drifts away, then basically, and Renzo is a bit right, because he says, even if you wouldn't do motion correction in your data, I think it would be tough if you include all 6 runs. But I present on Wednesday data where you have like 0.65 millimeter resolution at 10.5 Tesla, and the drifted motion is after 2-3 runs in 4-5 millimeter. So therefore, if you would just average it, all the columnar separation I want to do is all gone, right? So it's really important to keep that in mind. Why? And I'm saying it for one reason. Why? And reiterate also, John, why we need so much care about motion, about alignment, about all these things. Otherwise, I think we do really us not a favor. Another question I had prepared, which also came up a few times now, is the resampling. And there we already, in the very, very first version of BrainVoyager, had always the possibility to accumulate transformations into ones, as long as they're affine. And then you could basically make one resampling. Even if you first do individual steps, then at the end, when you have all these transformations, you basically go in one step. And that is something which is standard in BrainVoyager, and I will show you how we now extend this a bit to motion correction. And if I have time at the end, I want to show you some new things coming up, which include basically only one resampling from the raw data up to any space you want to go. Another sample pattern that I reuse, also a picture from Renzo, is basically how to handle training brain effects. And since BrainVoyager does not have any specific solution to that problem, therefore I will not talk about this at all in my talk, but I had to prepare this, but we had heard a lot about this already, and maybe you hear more about it later in the next talk. So now I want to go through some things which I think are pretty important, where we made, I think, some progress, but of course it's still a big challenge to solve all these problems which I mentioned, that the voxels align well, and so on. And the first is accurate segmentation if you want to go to the anatomy, and we will see later some pictures, not from this course, where you not see the gray matter well in functional data, so you need the anatomy. But of course, you can go both ways. So in all the alignments I discussed, even if I don't mention it, you can also go backwards, right? So if you really want not to touch your data, except maybe for things like EPI distortion correction and high-pass filtering, which you can, in some sense, combine, you can, of course, avoid some extra steps. But I will show you that you can go from the raw slices data in one transformation to this space, which I will present tomorrow, a 0.3 millimeter upsample space, because I prepared this also for basal, so that we can use that. But it's the same thing in BrainVoyager. Whether you keep, say, your data 0.8 millimeter resolution, whether you go in that space and do your analysis there, or bring the anatomy to the original data, doesn't matter. Or if you then add another transformation like upsampling, it's all one step only for resampling for most of the spatial transformations. So we developed with a very smart PhD student, Manuel Schneider, we developed to reduce the burden of PhD students to spend half of their PhD in manually segmenting many brains. We said, let's not waste time and try to improve things like many others have also done around the same time. And I'm particularly happy with the results we got, and we focus here on amplitude range, 0.7 resolution was the training data for that deep neural network. And it is a special architecture called tiramisu, which is basically a so-called UNet, which is used commonly for segmentation tasks. But it has some special additions to a standard UNet, which I will not describe in detail now. But in principle, that data set partitions the volume in 64 cubes, 64 voxel cubes, and basically feeds them piecewise into the deep neural network and spits out 8 tissue classes. As you see this actually here, if I zoom, do you see it? Oh yes, not sure whether it's zoom, but you see here, for example, that the input is one channel of 64 by 64 by 64 on the left side. This is the cube from one anatomical data set. One channel means the intensity, so it's just one channel, but it spits out 64 by 64 with 8 channels, and these are eight tissue classes, which it spits out as a result. So this is basically the input on the left side, and it goes all the way down to the bottleneck here, and then deconstructs basically the volume, but adds the tissue labels on the way up. This is then the out. And this tool works pretty well. So you get the 8 tissue class, and I want to, tomorrow I present this a bit more in detail, how you get the 8 tissue class, because it's very important that the network gives you probability maps. So you have 8 probability maps, which tell you what is the likelihood that a certain voxel belongs to a certain tissue class. We then, at the moment, convert this to discrete tissue labels, and that's a point where I'm currently working a lot on optimizing that, because, for example, for the problem, I come to a bit later, to get the gray matter CSF boundary, this tool, if you take the probabilities for CSF series, what it spits out, you can improve a lot when two cells are touched with this tool to keep them separate. Where I use other tools at the moment, but I might switch to using also this yeah. And here is just a comparison with other segmentation tools, standards in the UNet, conventional FSL fast, And basically, this TiramisuNet, at least in the data we had, outperformed these tools. There are also some numbers I don't have the time to show. But the important point is that this tool runs basically with an MP2 ratio, 0.7 millimeter resolution. Of course, if you have slightly different ones, we'll still accept it, or you have to rescale it or pretend that yours is correct. We will see this tomorrow in the exercise because we have 0.75 millimeter MP2 rates in the exercise data. And then when you start this tool, it basically calls into Python code, all transparent behind, because BrainVoyager has an embedded Python interpreter so that you can run any kind of Python directly from BrainVoyager. And you can also script and code a lot in BrainVoyager. I will not show you this today, it's too much. But in principle, you don't have to use the GUI for many things. You can use code for that. And it's also important that, you know, the whole code to run this and the whole network itself is open source. So it's actually installed with your BV-edu version. So it's everything transparently available. And what BrainVoyager is just doing, it just fills template Python code with the data you have, and then submits it to the tiramisu network. And that's actually the course data. So sometimes I show slices from the course data because I practiced myself once the pipelines. And you see, this is the defaced version I used. Then you can run the deep neural network here, can select MP ratio, MP2 rates, trained for both sequences. And then this is slow and the fast approach. The fast is sometimes good to just check whether it works in principle. But usually you should use the slow one, which takes on such an M4 MacBook Air, which I have here, about 10 minutes, and it's basically done. And here's what I alluded to earlier. You see here are 8 tissue labels, and it's not only created by matter. As I said, it's also CSF. It's a background label, and there are also labels for blood vessels and several more tissue labels we want to remove from the core data, like the gray white matter. And if this is the outcome coming then back to you, and then basically, so this is our data. You will see this yourself tomorrow. And then we have some post-processing, which I added to just, if you press run all, you will get them all run automatically, but I just want to tell you what they do. They convert is what I mentioned earlier. You convert the probabilistic tissue labels into discrete, non-overlapping regions of interest. We call them voice in BrainVoyager, volumes of interest. And that's actually what we see next. And then I don't show it, you see tomorrow in the course. And then basically we kind of use an automatic in the background running MNI normalization. There we know where cerebellum and some subcortical structures are, bring that back in that space and remove this pretty good so that these things are gone. Then it creates also volumes and surfaces, which you can use for inflation, flattening. Sometimes you have to edit them a little bit still, but they're usually already pretty good. This is the output of this tool after pressing the last 2 buttons or running all. You see gray matter outside view, and you see here the white matter view. BrainVoyager originally, before we had this tool, had this so-called advanced segmentation. This I only implemented originally for high field imaging, because when you really wanted to layerificate your volumes, basically what you needed was a good estimate also of the gray matter CSF boundary, because you see this in FreeSurfer, but also BrainVoyager. Usually, these days, with the good T1 data we have, the white gray matter boundary is not the big problem anymore. It's actually to really get a good, there where the cell site go together, get a good separation of gray matter in neighboring cell site. This is sometimes a big problem. Here's an example from our data, from the course data, and there are worse situations where I don't see anymore the transition between 2 cell sites. It's just gray. You know, you have the white matter, then you have just gray, and there must be somehow, because it's deep, it's not at the 3D where they really are gone, but it's really, I confirmed that, where you should see CSF, but you don't. Or here you see, if you look, it's gray, a little bit darker here, so I can see it visually, but normally it's difficult to automatically find that because the tissue contrast is very, very, very low. So, so therefore I still run, after that segmentation with the deep neural network, still run on top of this the advanced segmentation of BrainVoyager, which adds then some voxels, which, for example, here for white matter would have been missed. and it just adds them. These are the green voxels. And then you see here the outer boundary, which runs to certain stages, and then you get a surface which enforces kind of that, because it looks and assumes some information about the depths of the cortex and says, okay, if I transition and don't find the CSF, but I reach the other side because they're not 8 millimeter thick, right? This cannot be. And in the worst case, it just goes in the middle at that point and makes them there a boundary, because otherwise you get wrong layerifications. And that's how this then looks like for our data. This is when I write here course data. It means that's the data running this step using our data we have tomorrow. And now I want to switch to functional preprocessing, but I was also surprised that, again, there's a huge overlap between what Renzo said and what John said earlier. And for me, it leads to a slightly new strategy to do motion correction. Actually, might be possible in AFNI before, but for me, I used that data and the data I presented on Wednesday, which was even much worse concerning motion. You will see if you hear the talk on Wednesday. But it brought me to a new strategy. So here's the motion of our course data in BrainVoyager, and you see here the 6 standard parameters just extend from run to run to run 3. Then it's pretty stable. So run 3 to 6, 4 runs relative to each other have not much motion. And you see also BrainVoyager shows the frame-wise displacement, and you see it's not real motion, right? It's basically some drifts or maybe some sinking in a, and I talked to Steven before, and the 10.5 data I have, it cannot be that. It must be graded heating or something, because it goes over 6 runs. And you are then just 5 millimeter away from where you started, right? And they look into this now, and they said they had seen it before. So the strategy I derived from this and similar data is the following. It's a bit similar, I think, what you do with AFNI. So what I do now is I first run in a pre-step a motion correction just between the first volumes, or reference volume can be the force, the middle, whatever you want, and just look at the motion between these volumes before I do any motion corrections, just a motion detection step. And one thing I found very useful I came up with is not to do, say, run 1 with run 6, look at motion, because if you really have data accumulating many, many millimeters and rotations, it might be hard to align these. And I saw this in the other data. It failed. Did not correct the motion because it was so much off. And the idea now is I do this always pairwise. So the motion is estimated if you go from 1, 1 to 1, 6, 1, 1 to 1, 2, 1, 2 to 1, 3, 1, 3 to 1, 4, and then I just accumulate the motion. So I get 1 from 1 to 6, always easy because it's always pairs, and you can have 10, 20 ones, it will always work. And this is a small adjustment I did. And then later on, the matrices which are calculated, rigid body matrices, are basically added to a standard within motion correction. You don't have to do any, which BrainVoyager did before. You just said, okay, align to this one. And each volume had not to align only to the reference volume within one, but had to directly align to the reference volume in the other one. And of course, if you accumulate that, then it has to, motion correction is mainly for smaller displacements, not for 10 millimeter and 5-degree rotations or so, right? So in that sense, this strategy simplifies it so much that you do standard within run motion correction and then add the pre-calculated transformation matrices to go to your target run, to each volume. And you have only one resample. That's important, because if you do this, for example, with ants, I tried that, you usually do within first and then across, and then you resample twice, even if it looks good in many cases. So this is what I learned, and here you see what this tool spits out for our data. So if I start with run 1, 2, 3, 4, 5, 6, this means these are logical runs. That means the run 1 is here also the run 1, could be any other one. And then I ask the tool, show me what is the, before I do real motion correction, show me what is the motion between these runs, right? Then it spits out this and tells me, yes, the motion is particularly strong from run 1 to run 2, and then at least here for the Y translation, also for run 3, and then it's pretty stable. Same here with this rotation around X, which is the typical one, this one, right? It's the nodding kind of. And then it stops. So the last 4 runs, and here I did the same tool again. I don't show it, but you do it tomorrow. I then used run 3 as the target run, and then go to run 4, 5, 6. So you see the other runs if you say run 3 is the target run, you see that these 4 runs are basically without motion. Then you could do what Enzo said, you could just average them without motion correction, almost, right? But you see the other 2 ones is now 1 is 2 and 1. 1 is furthest away. So these are the ones now where we have started over here, right? So and that led me to select, or let you then easily select 1, 3 as the reference, is the one advantage. And it does only within run motion correction, adds the transformation, and then in one step gets you the, in my opinion, pretty good motion correction results. You can validate yourself tomorrow. Actually, for the VASO data, I analyzed not only the boat data, also the VASO data. I used the nulled VASO data. For me, this is not VASO. VASO is the blood volume corrected one. This I would call VASO. And this one I also analyzed and used there only the 3, 4, 5, 6 runs, just to make it simple. Yeah. And again, the prepared data, so 4 runs. Yeah. This is just to show you what I said earlier, that besides the runs, run 6 goes to run 1, is indeed what we need if run 1 is the reference. But you see there are also these not needed ones, run 6 to run 5. I don't want to go run 5, I want to go run 1. But this is intermediately used because it knows always the pairwise translations, and since they linearly add up anyway for rigid body, you can just add them, right? And then within the motion correction tool in BrainVoyager, there is now this new possibility. This is the old one, target func 1. Normally, you just gave the target run and the reference, which you see here. Here. And then basically it aligned any volume of your current run to the reference volume in the target run. And that worked usually well if the motion is okay. But if you have lots of motion and many runs and it accumulates, at some point it starts to take a long time. It needs more iterations, and sometimes it even fails. So therefore, in that case, this is for me a good development because now we have a kind of safe motion correction across runs. Also, you added that for the other data where we needed a mask. So you can also add a mask file now, and is for some cases very useful. Here you see, it's a bit fast, but you see here, this is run 3 motion correction. You see it's a little bit of motion, not much. And you see the difference image of the first and the last volume on top, where you see still these edges show there was still some motion within run. And after correction is basically gone. They look flat. That means there's basically no residual motion. Showing this for a run, it should be, this is 3. 3, yes. Run 1. This is actually I want to show you 1, because here the motion was more, as we had seen, more excessive, right? It's pretty good corrected too. So the difference images are also mainly flat, and therefore that's a good result. If you align them all together, they look very well. But if you want to be really on the safe side and have very little motion, just run 3 to 6 I would use. Actually, here are the conclusions. All volumes of all runs of the course data are well aligned to run 3 after excluding the outlined motion correction strategy, and the calculated across and within run motion parameters are very similar. And this I also did. If you do the boat and VASO independently, VASO now the null data, you get almost exactly the same parameters with slight deviations. That's nice to see because it's independently done, right? Yeah, and since the slab is so small, the motion around the x-axis, which is there, in this very thin slab, moves out visual cortex, unfortunately, right? You see, you lose like a few slices, and therefore the strategy to use the 4 runs with complete data is maybe not too bad. And especially when I looked in the statistics, the checkerboard is so strong, right? With your 12 repetitions blocks in 1 run over 6 runs, 4 runs are more than enough, even for VASO. I'll show you in a moment. API distortion correction, I will not talk much about. We have a tool in BrainVoyager, a plugin called Cope, correction based on opposite phase encoding, which basically implements the chess-up approach, which is top-up approach, and does this quite similar. Just show this here. Tomorrow you will see that we'll practice that, how to use it. So you basically check that your parameters are correct, like that you have APPA or LRRL, whether you have diffusion data and using a spin echo EBI, or whether you have bold data, you can also use a normal one. And then you have two different cost functions. You can choose, usually we use the default here, normalized cross correlation. That's basically it. Then you estimate, and here I use now the PA from the which I forgot in the first time. Thanks for reminding me to bundle this with the data. And you see here, you use the PA and one of the APs. You had only one. Now I have a question to you, Renzo. When was the PA recorded? Before the runs, middle or end of the runs?
Maybe after the 4th or 5th. Or
Okay, that's good, because
Yeah.
by line to run 3, which is close to 4, 5, 6, should be almost optimal. And then you get a so-called voxel displacement map, which basically estimates in each column the EBI distortion, right, for APPA, and then you apply this for the AP to your data, which is AP. So here are the 6 runs, and then you basically get them corrected. You see this here. The left is the PA. This is the AP before correction. This is the AP after correction. This is the so-called voxel displacement map. You see mostly happens here in the front, which you also visually see here, and a little bit just after, also in the visual part, but not much. Mainly you see only most changes are here in the front. This is corrected here now. Next nasty problem, functional anatomical co-registration. I think in BrainVoyager, I'm a great fan of Greaves Boston developed boundary-based registration. For linear co-registration, the version I used implemented after the original paper, which was very clearly described. 1 weekend I could implement that, it was wonderful. And basically that works extremely well also for our course data. But I show another approach I tried. So this is just the idea of BBR for those who don't know. You basically project a white matter cortex mesh into the functional data. And if you would have been in perfect alignment, so the yellow line is a cortex mesh, and in the back you see an EPI slice of your functional data, right? And if the two are aligned, you see what we see here. This is the aligned case, right? You see there is perfectly going in the functional data, not the anatomical. That's trivial because you derive your mesh from the anatomy. If you project it back, it looks perfectly, right? But here it's in the functional data. And then you see how this works. It basically around each projected vertex, which is here the yellow line, it goes along the normal, so orthogonally to the direction of the surface. And it samples in the right and the left. That means in the white matter and the CSF samples intensity, right? And subtracts those. And if it's always, the surface always has white matter on the one side and gray matter on the other side, which is the boundary, then you would add up always in the same difference sign. You would sum up this as a cost function, right? If you are misaligned, sometimes the one side is higher, the other is lower, so you cancel a lot of these additions or have very small values. And that's the cost function here. You basically try to maximize the difference between gray and white matter, and it's maximized when you basically are exactly on the boundary in your functional data at the two sides, which you see here graphically on the left side. So we sample on both sides, make this subject. This is the original equation from the paper, BBR paper, as the cost function. And you basically stop when you find the minimum of this cost function. Here's an example how this looks like. So here you see the pink or violet lines here are displaced, at least vertically. I see it with my own eyes, maybe also rotated. And this initial alignment comes from, usually if it's within session, from the header-based, DICOM header-based alignment, right? You can bring it roughly to the right space, but you do not have corrected then for any kind of motion between the two recordings. And then you run BBR, and you see that the quality is really good afterwards. And this is not a high field. This is a standard 2 millimeter kind of scan. I don't know the exact resolution, but a standard functional one. And it's working well for partial brain coverage and especially slabs. That's one reason why for high field stuff I always use BBR because it handles very gracefully the small slabs. You need the initial alignment, but then it works well. And here is the output BrainVoyager gives. I mean, it's just cut a bit the text, but the important point is the cost function. The cost function at start is 1 point something. then it is a grid search, because BrainVoyager, without using really a fitting procedure, but just make a grid search, and then it finds already a decline to 0.49, stops then, starts the real minimization function with an if-Marquardt approach, and then basically finds a number below 0.1, which is excellent. That means you have really, really good co-registration. And yeah, that brings me to the point that what I said earlier, I mean, you can script these things, but here is it in the GUI. You can then say, bring my functional data using the header-based alignment, followed by what you just have seen, the BBR, followed by another ACPC step just to reorient this ugly MP2 range was shifted like this. I don't like this for aesthetical reasons. So I just oriented it straight, right? And then did the 0.3 upsampling. And this is all combined. So all these steps you see here are all done in one step. This I try to say, right? All these intermediate steps are one transformation step. And another thing which is good when compared to ANS, BrainVoyager has some tricks. It uses so-called sub-boundary, sub-cubes, sub-bounding boxes for the functional data, which makes the data not excessively growing, which experts using ANS complain. And there's the good news. I'm currently working on getting familiar with ANS and working on integrating this directly in BrainVoyager so that you can do the ANS registrations or ANS application by direct calls without going first out in data, reading it in, and it gets much less memory blurred than this. And you can bring in the full time course, not just a T-map, but you can bring your 6 runs. I did only one average run, but you can in principle bring all your data now in any space you want. That's nice. And it's also because of this here, because when I upsample the data, I can tell that the functional data should have a certain relationship to the anatomy. That means I don't maybe want that my functional data is upsampled. I can, and I just click this one by one, but it gives you 8 times more per volume data, right? In BrainVoyager, because if I already with 2 upsample the data from 0.8 to 0.6 in any case, and that seemed to be good enough because you interpolate at some point anyways, and I have not seen a big change if I have it 1 or 2, so I recommend 2 because it's just much less data, and you don't have to do that. It's just if people want to have their data in that space, then you can do this in BrainVoyager because it's quite graceful with these memory considerations. And it affects also time a lot. So here's now the result for our course data. You see our slab. And this is not the EPI T1, which I didn't touch. What you see here is the trick of VASO, namely when you have then corrected the VASO data with the bold, the null VASO data with the non-null, you get a really beautiful T1 if you average over time. And this one I used for co-registration. And basically, you see yourself how well this fits. Although I even forgot at that moment, it was before you sent me the email, I forgot the PA. I didn't see it the first time, honestly. So I did this co-registration even for undistorted EPI, right? And you see that the alignment is still pretty good, and it was smart enough to be not perfect in the anterior part where you saw a lot of big displacements, but in the rest to the visual cortex down, it looks actually super good, right? So the quality of alignment is good even when you forget TBI source. Even more surprising is what I show you now, because I have not yet ANS integrated. I run it outside. I just want to tell you that we'll not talk much about ANS today because we don't use this tomorrow. But you see here, also forgot to do the EPI when I run it, right? Now I have done it, of course, for the course. But you see here, when you look at any point you want and compare our slab versus the MP2 range, you see basically no difference. Because ANS is for me the most powerful nonlinear alignment tool which is out there. And therefore I'm eager to integrate it now into BrainVoyager. We had used it in our work, of course, before, but running it outside, not in BrainVoyager. And the big advantage is, again, that I can, when I do it internally, not resample the data. So normally you go out, run top up, run ANS, and then you have resample the data, and then you go to the next thing. If you have this integrated, you just do these steps and make one resample for all of those things. This is the big advantage. So now I come to the core, depth-dependent cortex modeling. And yeah, here I just start with the question, and as I mentioned earlier, if you look at the right side, when we zoom in and see the small voxels here, and you see the colors below these voxels, it seems almost impossible to know where these voxels are in depth without a reference like an anatomy. It's not totally bad if you look here in the in this slide. You see, of course, a little bit of BrainVoyager matter, but it's sometimes really hard to say where these voxels are falling. And in that sense, as long as you don't have, like for example, Meso, where you have a high T1 weighting, it's important to do good co-registrations. And as John and also our research team used surfaces a lot, we were very proud. I remember this one reason why I went to fMRI, one reason was Serino's maps in science. That was for me the day I said to my boss in the Max Planck in Frankfurt, Wolfsinger, I won't stop these monkeys, I go to human fMRI. Right? This was it. So I was completely addicted to these surfaces. And we were so proud that we could model it as a sheet and then project our data on this. Wonderful, right? You see flattened everything. This is cool. And now we know this is not enough because we have depths now, right? So we need this, of course, Jonathan knows, we need depths that could be in what we call a BrainVoyager mesh approach, and we have the high resolution 3D grid approach. I will show you both in a moment. I will not talk much about this because we don't use it tomorrow. We use only the grid approach, which for small regions and slabs is the more preferred approach. And I start also what Jonathan briefly alluded to with the Laplace equation, because as a starting point for the equidistance and equivolume calculations. And I think in the paper of Jones, this was nicely described, because if cortex changes thickness along the cortex, it depends where you start to measure thickness, what thickness value you get, right? And I really liked it very much to use here the Laplace equation to basically calculate the streamlines and the equipotential line, surfaces here, because then you get at least, sometimes curved, but you get at least a unique thickness value. From one side, you come to the same point on the other side, and when you start there, you come back to the same point. If you don't do this and go just straight, and that's what's indicated here, you come always to another point, so the thickness is not unique. See, especially here, you can have a smaller or a thicker thickness. So this is something we use in BrainVoyager, and we calculate the distance metric, and this is from the course data. This is our segmented amplitude range, and we run then the cortical thickness tool, which is selected here, a distance measure from white matter to gray matter, right? So it shows you the distance measure in the volume. So now what is the difference between these two tools? Why did I do this Euclidean volume grid approach? Is the cortex mesh not enough? Before I do that, I want to stress one point, because the viewers, we talked about the viewers. When I published, or we together, the team, published these columnar papers, because I was focused at the beginning more on columns, although I needed layer to show whether we get consistent data across depths, right? So it was always both, without smoothing, as I said earlier, neither in the layer nor in the column direction. But the important point was always from the reviewers, your data is a bit noisy, and maybe there are no columns, or columns have no meaning. And it was always hard to discuss with them why I'm not interested so much whether it has meaning or not. I'm just happy and pray to nature that we have columns. That's the point. And some reviewers accept, some not, unfortunately. But you see, if the neurons with the different preferences would be randomly scattered in the cortex, you would have no chance to image that with fMRI, even not with 10.5 Tesla or 14, which we built in the Netherlands. So we need this kind of clustering of neurons doing more or less the same thing. Of course, any electrophysiologist tells you it's not really the same, but at least they are more similar within the column than to the next column, and certain features change them really quite substantially, as we know from orientation columns, for example, in B1. And another point is also that when we say, yes, it's true, our columns don't go always completely through the data, that's also in mind of the viewers that don't read the electrophysiology literature, although they claim, we know from this must be going all the way through. If you read the papers, they say, oh, columns are skewed, half only. So there is not this perfect column. Maybe we want, I don't know, but not in higher cortex. And the paper with Zimmerman was the first extrastriate columnar paper, and we didn't know what to expect, because also the penetrations from Newsom, Albright, and people were so sparse that it was difficult to expect, to know what to expect in the human brain. So therefore, the world is always more complex. But this is, I think, an important side aspect. When do we reach a point, and I'm looking forward to that, when we can tell also electrophysiologists, we found this is the organization of that area, and they believe it. They say, okay, we didn't have seen this like this in the monkey, or so maybe in the human it's like this. So we always, at least in sensory areas, always run behind and try to prove and validate that what we do matches what we expect from the animal. But we need to go, and of course there are papers also from our lab going beyond that, but nonetheless it's tough sometimes that people trust that you really found something unique in the human at this columnar laminar stuff. Yeah, this is how this looks in BrainVoyager. It's very similar, I think, what John is doing in FreeSurfer. We basically have a mid-gray matter mesh usually, and then we go towards the white matter and desample by going to the normals and resample, and each steps move the vertices there and get then a new mesh. This I want to say. Right. So this is, I call it the whole mesh, entire mesh approach. You know, we have this very irregular triangles to sample. And I was not happy with that, because sometimes smoothing, everything looked, if you have an area where they're quite packed because it's complex curvature, they look differently sampled than in more straight regions, right? And therefore I was not happy with that. That was the main reason why I went to this regular grid approach, like I call it. And especially when you have, this is when we work with 3D Grace, also with Federico and with many other people. We basically had a smaller slab, maybe like the slab you have in your data, but what I get now from 10.5 is actually much thicker. But still, when we use these slabs and are only interested in a small part like this one here in this data set, then it's also not needed, like Renzo stressed, to have a full segmented and full-blown mesh, because you might want to just look at this, had exactly the same reason at the time to do the grid approach. Because it was just there, just run it there in 5 minutes and I see my layers. It was not so different than in Laney philosophy, right? And this was the other reason why I did it. And here I contrast the two approaches a bit. So on the left side, you see that I start, say, with a mid-gray matter mesh, and then I go along the normals, and then create at other depth levels a copy of the same mesh, and then can sample data from these different meshes. So what is different to the, here I call it Cartesian grid approach, but doesn't matter how we call it. The idea is actually, and that's the point which I want to make to also Renzo, it's basically calculated completely in the volume. There is no, I can visualize this grid in the surface, in volumes, whatever I want. But the calculations are in the volume, because it's still, also Farouk says, I know yours is the surface. I said, no, Farouk. And soon make it, the code of this available, so you can read it yourself. You will see no relevance to the surface, just to say it. And it's fast, so you get also very quickly your results. But why I did it is actually basically have here this vector field of the distance metric, and then basically start here also at some usually mid-level here, and then basically reconstruct new, you could call them meshes, but it's just numbers in principle, right? You could call them meshes, but it's just a new creation of meshes at an arbitrary fine resolution. Basically, my solution at that time was similar to your upsampling without needing to upsample, because I do the upsampling there where I need it. That's maybe the biggest difference. But it's the same. It's funny that when I always smile when I hear you talking, because they were basically all the same motivations for this approach. It's just a bit differently implemented, but it's very similar. And so you go then in one direction in equidistant steps, and then always sprout from each equidistant step another orthogonal line. So you get basically an Euclidean partitioning, a very clean voxel, honest, in principle voxels, because you connect them also to the next one, slightly, not fully cubic voxels, slightly different. But in principle, it's a voxelation at high resolution, you know? But it doesn't suffer from from this, what you have, you would then have these kind of, I don't have this because I start already in this vector field and get smooth Euclidean meshes, I say it now, right? But it's funny because we still discuss this over years. I think, yeah, I showed it often as meshes. That might be the confusion. But you see now, we also implemented, of course, the equivalent in this approach, and it's very elegant. Because when you, anyways, have your crit calculated, say this is the one crit step here, right? Then you basically have to have, if you follow the normal or the Laplace slightly curved thing, you basically find the area here as a very simple mathematical thing. Because it's a regular grid, you just calculate in milliseconds. So I know immediately how to have to shift this in this frustrum, it's called, to make these partitions equal volume. Super simple calculations, so it's super fast. It's not slow because people think, oh, you do meshes and it's something slow. No, it's super fast, all in the volume. It's just within the volume, I create these kind of representations. And all the details of this are described in this paper by Valentin Kemper and us. Yeah, you can find it there. And this is, I show it here too. You see, here are the grids, very smooth, without being limited by voxelation. And here is, if I want, and as even a function in our tools which don't produce any surface, you get this kind of layerification, or equidistant equivalent. And here you see just some examples for different small cortex patches. Straight one is boring. Here you see this, just these two layers. And here you see the connecting lines which link the corresponding vertices in these frustrums across depths. Here's three grids, 2 layers. Here it's, I think 10 is actually with Federico for an auditory experiment. And you see here how the grids go over a larger extent. That's basically the maximum. If you go further, it will not work because at some point, you know, because it's more for smaller regions. This is already a large grid approach. And then, of course, you can sample functional data on these grids, and they are quite regular and easy to interpret. And this is from the course data. Here we are now the 0.3 space is a amplitude range straight aligned and upsampled. And here I just draw in 2 minutes, again, similar like you do, Renzo, just draw some regions and sample from them functional data. These are the 2 regions of interest. Then I basically, can do the grids. And here I show you first, I don't do the grids. I just load the thickness map, which I need for the distance metric. And then I go right here and set depth spinning in non-overlapping voxels, can say how many. And then I get, just without using the grid approach, just like in Laney, very similar. The depth spinning, you see this here. These are actually the depth spinned layers without using the grid approach. You don't need it actually. And then I sample them from the layers, average this, and get actually, I should say, this is the basal data. So it's the corrected by bold basal data in the data from Renzo. And it's so the real basal data. And I haven't flipped anything, just to show in the course that it's really going down and not up, right? So you see here, roughly in the middle, in the early visual cortex here, you see really a nice dip here in the basal data. So it's a profile. You see also that the alignment is good because you see mostly that the functional data follows nicely the gray matter. And that is something, was not the second reason why I did the grids, because I can switch to volume again, but very easily because I have a volume, right? All the grid points you can just stack because in principle I reconstruct it, but in principle, you know, the flattening is without computation. You just go to the grid points, make them ordered in the plane, and then you have basically your voxels created again. But this is a voxel space within this nice equi-grids and not in the real voxels. These are newly created voxelations, optimized for sampling, right? But you have then your layers and columns, as you see here. and can sample it. I think that's another advantage here, or at least another approach, which might be very similar. And you see here, sometimes you get beautiful columnar structure, and you see now why I cannot smooth. The horizontally smooth, these two guys here, you would just blur away my effect. Right? This is just another example showing this. And here is a little animation that you can nicely make the gray matter, which you see in gray, more or less transparent to see more or less internal structure, right? And but the nice thing is if you have volumes, you can apply all volume tools, right? So if you are on the surface or in something, you can apply surface tools, but some tools are more used in volumes, right? At least people are happy to have this in the volume space. So in that sense, there are actually two different ways to go to volumes. One is to do a straight binning, similar like in Laney, and there it's good to upsample your data. For that approach, you don't need principally upsampling. It's good to do it. I actually like it now. I do it regularly now. Go to 0.3, so I can run Laney and compare. It's very nice. But if I have this, I can make the gray matter transparent, and you see, and you would think, why is it so many gaps? Because these are just selected 2 features of 8. So the other one would be filled by other features. Just do it to see more. Otherwise, it's just we don't see much. Yeah, and finally, it's important to point out that all the calculations are exported in a binary file or documented in a text file, so that you can do some custom processing. So if you have for all the grids or bin depth things, sampling your voxels, then you can also do these scatter plots and all the things. And the nice thing is, since you bring all the functional data also in that space, you can run in a very modest computational load, because you only get the time cost to these sampled grids, vertices or voxels, however you want to call it. It's a bit an ambiguous representation, I would say. And then you can run statistics on the time cost for each of these in this cube or whatever you want, because it's all exported and you can use it to make custom analyses and custom plotting. Yeah, we had seen that. I just want to show in the Mookie paper, this grid approach was, for example, used. We have heard about it. I don't go into this. In the Motion Zimmermann paper, the grid approach was first time used. Right, so it was developed months before we did that. I would say in 10 had this ready, but then it took publishing this a bit longer. And the nice thing is, which really convinced me that this is a good approach, not the layer approach, but going for columns, not only for layers. If I, for example, selected the horizontal, vertical, and oblique features, and plot their time course or their t-values, you get basically profiles for the different axes of motions, which is this here, right? Which resemble very, very nicely what you know from a card monkey. Again, I do this not only to show this, but it was nice to see it falls out very precisely what you would expect for these behaviors. And that's a study probably have seen. It's a study where we used only horizontal, vertical axis of motion, but we showed in this ambiguous stimulus here, and that's a more high-level application of this stimulus. Doesn't run now, not sure why. Just click no. No, doesn't matter. But you have an ambiguous one where you see either horizontal or vertical, and then we could see that the horizontal columnar clusters mapped before were more active when people say, now I see horizontal, and they went a bit down and the verticals went up when they switched and said, now I see a vertical motion, right? But it was all in their mind. And we could track the conscious percept of people using columnar resolution. And this used the same grid approach, for example. Yeah, this I think was all I want to say. Optional slides, maybe one. Maybe I'll show one. I alluded to this already, right? So I'm currently fallen a bit in love with ants. So I'm going on with that. And it's will also be in BV and BV Edu version. You have the 24.2 beta release. In the final release, this should be complete. We don't use it tomorrow. I just call it now mainly outside. but I will have it integrated then. And I also started work after talking also with Farouk, who is, as Enzo said, now the main or co-developer of Laney in my company. And of course, I'm a great fan of Laney, otherwise I wouldn't support it. And for me, it's important that these two softwares work well together. What you do with AFNI, I will do also with BrainVoyager. So in the sense that basically Laney routines and people can then choose and or compare, which is always good. Do you see similar results? Whether you use, let's say, the grid approach or use the Laney approach, right? This would be nice. So you have more confidence in your own data. And then I start also based on the free software we have called BrainViewer. I will add there the free Laney, but also the free version of many BrainVoyager tools, especially for the layer analysis. The grid tools also open source, so that basically people can use these tools in a nice GUI, also with Python scripting. And basically, I'm just now thinking about a name, maybe layer-Voyager or lay-void. I think layer-Voyager is more my style, so I will probably use this. And the nice thing is that this software then will integrate parts of BrainVoyager, Laney, and ARMS. Thanks for your attention. Questions?
I have a question. I'm sorry, I was not here in the morning, so and because Rainer is up, I'm going to put up my wishes, my list of wishes. In the data that you all have looked at, I haven't looked at them. How much do you see the problem that between one run and another is not just motion, but the fact that the distortions are different? So, so when you have that level of excessive motion between, let's say, run 1, 2, and 3, my experience is that what often happens is that the distortions are not the same. So having only one PA, which we all decide to do, I think, for time matter, that's another wish I would have for ISA instead, that there should be a PA, 5-volume PA at the beginning of every run. But when you don't have that, then doing PA only in the middle is not that great.
But this was the data. Did you hear what I asked Renzo? When did he do the PA run?
Yeah.
So because the run 3, 4, 5, 6, you have basically not much motion, and it was around there, he said. So therefore, we are fine for that data.
Well, for 3, 4, 5, and 6.
Yes,
and not 1 and 2, no.
No, that's the point. That's the point. And since this paradigm, I mean, it still looks pretty good if you motion correct it, but of course it's not perfect. That's also the reason why I look into ARMS at the moment, also for motion correction, because there you get these things better resolved than having a rigid body motion correction.
So do you? So my question is then that's where I come at this question. I think that one way that we try to solve this is that we try and combine. So what you have come up now with as a solution, which is like you do within motion correction, within run motion correction, primarily you do between to just figure out what the between is and then reapply them together. But then for the runs where you do see this is not enough, like after this, they are really well aligned, but the difference is the distortion, then at that point you need nonlinear. So with your integration, are you thinking that it will be possible in the end to actually combine the linear steps and the nonlinear one in one go, like in one?
That's the goal. I talked with Alessandra exactly about the same thing. She's annoyed about how Goebel and ARMS handle data. And therefore, she is limited to do this in 2 steps, or it's massive amount of 100 gigabyte or whatever you need for the output of this. Because I tested this myself with ARMS, and it's true, if I would use ARMS tomorrow, it's the reason why I don't do it. The file which comes out is 60, 70 gigabyte. Right? And I'm not sure whether you want this. One file of many files, 60 gigabyte. And the reason is to integrate ARMS in BrainVoyager. I can avoid this 100%. I use the applied transform after I have the registration, get this 1 giga file, that's just one from, in this case, was 400 volts because I used the Vaso data, you know, and then use the BrainVoyager thing. In this one step, I make my bounding box, I make my 2 by 2 by 2, whatever you need, and then save that. And then the file is as big as usually in BrainVoyager, which is more handleable.
But the biggest thing is also avoiding, like, I think the interpolation analysis sometimes, so I can have the feeling like the resulting interpolated data is different than when I run the interpolation outside of bands with the same tools. for the same month, let's say.
If you use the same parameters, which are of course are called nothing else than plain ans. So it's the same. So if you use the same parameters, you have the same result.
Yeah,
It's not
for
changed.
you, the concept is that you will be able to interpolate that you have 2 by 2 by 2.
And the bounding box.
And the
Yeah.
bounding box
Yes.
using your interpolation tools and
Yes.
let's say, but using also, let's say, the nonlinear displacement map that ANS gives you.
Yes,
as a-
exactly right. If you want, you don't have to. For example, if I hear this data, I'm quite confident because this checkerboard is so strong. It's enough to stick to run. So this pre-analysis gives you that information, right? You know, if I do a normal motion correction for the runs 3, 4, 5, 6 and align them all together, even ANS doesn't do better. But if you have run 1 and 2 and you see more things where the residual non-linearity is there, of course, if you say they're not where I'm interested in, it's fine. But if they affect the region you're interested in, I would use ANS for sure. Yeah.
So the grid-based surfaces that you're trying to make, so basically you're trying to solve the issue of like more dense sampling in one area compared to the other based on the triangle meshes, another software, right? So couldn't you do this with like triangle meshes with uniform edge length? So any particular reason you use like a square grid data structure?
You could, in principle, try to change your meshes to something more regular indeed. But since I wanted to focus anyway on a restricted region, I wanted to really recreate this from scratch there because it was more logical. And the mathematics I then got is so more easy more tractable for laminar analysis. If you start with meshes, I'm not sure, I didn't try. Maybe John knows how difficult that would be, what he says.
It's a little tricky, actually. Yeah,
Oh, is
I
it?
mean, because again, you're trying to represent some sort of continuous surface, you know, and so remeshing, while still representing that kind of surface accurately, requires kind of repositioning sometimes of the vertices, depending on whether you add vertices or subtract them. You could just upsample the mesh, you know, but then the file sizes get, you know, pretty large and hard to work with.
But you would still need a very dense mesh to represent like compared to like a triangle or a square. So I think the mesh density would still remain the same
Right,
or
right.
similar.
Yeah, exactly. It's more that it's easy to just upsample mesh. That's kind of the brute force approach. It's a little bit harder to resample such that you have kind of, you know, whatever kind of consistent mesh density, again, because you're moving vertices around on the surface. Not impossible, but a little tricky.
One fundamental problem you come to is non-Gaussian curvature, because that's the reason why my approach stops at some point, because I assume you have regular grids, Euclidean distances and everything, so you can calculate things fast. But of course, if you extend it too much, have Gaussian curvature, it will break down. So if you would have a regular, more irregular spaced vertices in a normal mesh reconstruction, to move them around and maybe say, oh, I have not enough because I need one more, then you have still somehow start maybe to remesh it, recreate it. I'm not sure which is then the faster, better approach.
The other thing, I don't know if you were suggesting to have uniform mesh length, so, and then different number of vertices across depths, which would be a problem because then you lose the one-to-one relationship between depths, which is what many of these approaches want to keep, right? So one nice advantage, and I do remember why the grid sampling came about, was that we wanted to have so the depth relationship. So this vertex goes to this other vertex, goes to this other vertex, but then the grid also had the advantage that then this regularity was also maintained within the layer, within the same layer, so that you knew that moving in one direction in the layer meant the same thing across all other layers. So that we could analyze it in fact as easily flattening and making it straight, and then having a very regular spacing that would be like that. So that was the idea that Werner had by now more than 10 years ago of making like that. It only works with small batches. And the point I think also of the vertices and what Researcher does and what we can do as well is that with all the caveats of what having meshes is, you at least maintain the fact that the mesh of that depth and the mesh of the higher depths, they are in relationship with each other, which is extremely useful on the majority of the analysis.
I should maybe add
Really don't want to lose that.
No, but I should add that the parameter has two approaches. You can select it. One says keep the same grid and then expand your square, so to say.
Yeah.
That's true, but you keep then the rest. But it has also the approach, if you want, say, I don't care about that, which I did before, maybe for the equidistance. It was not so crucial to have the exact same correspondence ones. And it was before I did the volume, which is the layer cake from Farouk. It's very inspired by that, right? So in that sense, at that time, I just could also resemble it that if you are at the upper layer in the Celsius, right, you would have here more regular grid elements than here, because it's short on distance, right? But then, especially for the equivolume, we wanted to keep that so that we could very easily, these are our automatic columns without doing anything. Any connection of one square in depth, which then would fan out if you have a Celsius, would fan in if you have a Travis or the other way around, that basically you get all for free. You do nothing. That's the cool thing.
Yeah.
Right?
Yeah, I agree, and it is very nice to have these like automatic columns, right? But when I meant like uniform meshing, I meant like on the one surface. So if you have uniformly spaced grid points,
And so
it could be
this I can tell
triangles.
you that in BrainVoyager you can get that automatically. So
Oh yeah,
it's a-
definitely, yeah.
there is a way so if you want, after you've had your high density mesh, and there will be some misplacement, and I think, and now I'm talking for the software that has been written by Rainer, but there is a way, that's a trick, which is a trick to go to another step of BrainVoyager that is called the space alignment, where you can resample this mesh or remount this mesh to a regular mesh. Now the triangles will have all the same size, and so that has that. But it has the issues that Jonathan is talking about. This operation is still quote unquote difficult, right? So it's good for certain things, bad for others. So what I use it for is that if you, for example, have an atlas you want to bring into these spaces, then often you want to have that because you have the atlas in space that is already on a regular mesh, and then you want to map your mesh to the regular mesh in some way. So I think these things are already available as tools, except that they have drawbacks, right? So they aren't perfect. There will be places where things are tricky, like Don almost said. So, and you need to decide also the density of the regular mesh. So which density are you going to use? So very high density, very low density.
But doesn't that also apply to this? So how do you decide the mesh density?
Yeah, exactly.
So that's decided based on
Yeah.
the voxels, right? That,
Yeah.
that for meshes and for grids is decided based on the spacing that you decide to have. So if you say move of, let's say 300 microns, then it moves.
Then you can calculate the,
Yeah.
that's true.
Yeah, you want to capture the geometry. Yeah,
Yeah.
I think Suma does something like that, right? Doesn't Suma have like a kind of standard mesh, defined on a sphere where it's easy to kind of make
Yeah,
things
so-
like some,
So it is.
It's like Visual and Dale's approach, a similar framework, of
yeah.
course.
But yeah, so it's like, again, it's like a uniform mesh on the sphere, and then you kind of work, so it's kind of consistent across individuals, but then you bring it into native space, you get the
Exactly.
regular again.
But also what Federico alluded to, you decide, this is grid approach at that moment yourself, what will be the resolution, so you don't have to decide to go to another mesh, which is still not also so like quadrilateral. So it has still, even if it's more regular than a normal reconstructed, because you have used an average basis for calculating them originally, or use a sphere, but even if the sphere is folded, you again have quite better than, I'm still not solving this. So I think for that problem to say, I want for that region in the brain, a good mathematically treatable regular meshes, the reconstruction, I think, is still a good way to do.
I think that the biggest advantage is really like you are 100% sure the relationship between layers and the distances like that. If you do these remappings, for example, I use them sometimes, I do use them still now, but then I definitely don't look at columns. So like I already know I'm not gonna look at columns, all I care about is just layers, because the relationship in the vertical direction is just challenging. Even if you can force it to be there, there will be one, but it will be less, let's say, accurate than regrowing something according to the relationship.
Enzo, you had a question?
Yes, a personal question, if you don't mind. Or maybe first a personal comment. I'm digging the layer-Voyager, and I'm excited about both the kind of this optimized slab motion correction, but also seeing VASO data in BrainVoyager. Maybe the personal question is, kind of you're a busy person, right? And you took weeks to prepare this, and kind of what's driving you? How kind of why do you take kind of these chunks out of your time to still be coding and kind of aside of all the management responsibilities?
Not so different than Farouk is. When Farouk did his PhD with Federico, he came to me, Rainer, this research careers at that time. Today he says different things. But at that time he says, Rainer, I'm fed up. I don't want to hunt paper, precision. Can I work for you? He said, sure. Can I do what I want? Sure. So he got to this because I think he's brilliant. He said, whatever he will do will be good. You know? So that's how I hired him, just that you know. And he is passionate about coding. It's the same here. You know, when do we get reward? We wait until the review goes through, it takes time, right? If you code, you know yourself. If you code and solve a problem, if you have people outside, this guy keeps me busy also a lot. And then you solve someone's problem, this is reward. It's really reward. You get it more frequent than this. And I'm just, I studied computer science because I was already in my young years completely addicted with programming. But my student money, everything was programming. Right? So it's something I need. It's like meditation for others or something. I need this because, any free time I have, any free weekend, any day or time, flights. I wrote a nice tutorial. It's not ready yet, but it will be the version tomorrow. And I really get fun out of coding, and I get fun out of problem solving, and I get fun out of helping people.
Maybe I have another less personal question. So you mentioned the lack of smoothing several times it's received. What is your point, or what's your view on SNR? Kind of we are at the borderline of what's visible and what isn't, and kind of how do you think about kind of denoising, or do you lose something, or
That's exactly like I look now at Nordic data also, and I was originally very skeptical. Actually, there's a paper with Alessandra which ended up at the cover at Cerebral Cortex. We first used Nordic at that time, but we had not the phase status. It was not the best version of Nordic. And I saw it wipes out partially my effects I'm after. And Alessandra confirmed that by we analyzed everything very carefully and said, you're right, we shouldn't use Nordic. So and then I decided not to use it anymore because I had once a bad experience. Now I get this data from Steen himself. He applies the Nordic, and I see the benefit. So I'm now not a fan yet, but I start to see the value of it. But as soon as you have things which are very close together, I'm very skeptical about denoising when you say if the voxel is not doing the same, I want that the voxels are not doing the same. It's like this layer smoothing. This is exactly what I need. So therefore, I still check and check and check. And I saw also that the effect size of the direction of motion study, which I did here last year for 1.5 subjects only till now, Nordic gets much nicer results, but the differential activity is maximally as good as when not using Nordic. Maybe worse. I have to do quantitative analysis to know this. So therefore, I remain skeptical. But in principle, you're right. I love Vaso, as you know, but we lose another 4 times or whatever it is signal to noise, right? And contrast to noise. And the problem is for more complex tasks, which I'm very interested in as a cognitive neuroscientist, right? I love perception, but I like also cognition. Like this paper with Marian Schneider, which I think you know, with the tracking the neural correlate of consciousness. This was one of my highlights for myself because I could show myself, yes, we were always on the sensory thing, or I would like your working memory paper with Finn. These are highlights because they show we might be able to say something, give something more in understanding the brain for more higher level cognitive functions. But this is really tough because you will have reviewers who don't believe you at all. I can say, oh, you make a too big jump now, right? And therefore, I said it earlier, when is the time that we, from the sequence side, from the analysis side, we can say in confidence, you have to trust this data. That is how it looks like there. Like when you now say this condition is stronger in MT or in phase area than that condition, people just accept your paper, right? But when can we say the column 0.5 millimeter away or millimeter away does the opposite than the other one? When can we publish this in a new area? There is no monkey who has ever in that area studied for columns or layers, but we find it. This is where I want to be. But we are not yet there. there yet. Not yet. But signal to noise would be then even more important, because when things fluctuate and you cannot say, okay, then I make 4 times as many trials, blocks, right? Like you have wonderfully done with the checkerboard, which killed me. I've never seen so many repetitions of a simple checkerboard. I said, how can they do this? And this I have made a nice study, right? Just kidding a bit. But what I want to say is, for that, yes, you can repeat this passive fueling. The brain will be stimulated always more or less the same, right? With some fluctuations, but you average them quickly out, and then you get a beautiful result. But if you go to attention, there are later papers I know, but with Vaso and with Sebastian Vesbach, as you know, you are involved in that work. We tried event-related Vaso, and it worked pretty well. But if you now tell people you need about 10 to 20 trials, and then they have 5 conditions, no, and then I go back to EBI. So that is the problem. We have better tools, we have better sequences, better tools, in my opinion, for what we want to understand of the brain, but it scares away still people to make this extra effort, this extra mile, and that's sad to see. But it is like it is, and therefore, anything which improves signal to noise, I would love, of course, everyone, because it would make more complex studies possible.
Can I ask another question? And they lead to all of you that are presented. So, I mean, what extent you still believe that from that perspective, getting a right segmentation is really big bottleneck of. So, how much are you happy with the segmentations you get automatically from any tool? So you get the best MP to range that you can get. You just run whatever automatic tool you like. On a scale from 1 to 10, how happy you are with this?
I mean, you just maybe very brief, because it was due to Federico that I found a bug, not in BrainVoyager, by the way. But he came once to me and said, I don't know, the segmentation doesn't work anymore very good. I said, cannot be, haven't changed anything. And then it cost me a week and I really did sleep. And after the weekend, I knew what it was. NumPy, because we call it via Python, TensorFlow access via Python. NumPy changed the precision. Not that you specify, Python is, of course, not typed, but it was clear that you could force it to use a certain precision for the neural networks, right? And then NumPy decided, oh, we estimate what is the best, depths of numbers, right? Resolution. And then we changed this as needed. And TensorFlow accepted that, and they got massive critiques afterwards, right? And the problem was that if you train a neural net with exactly this, say, float numbers in our case, now we have maybe double or whatever you have, it sounds nice, but there's small changes. And in the network, deep neural network, this adds noise. And this I figured out is the problem which Federico has. So therefore, in case someone wants to install this tomorrow and wants to run yourself with DNN, you can, but I have to get the step also, you can jump over it. You need to install in Conda, one line, the right TensorFlow, the right NumPy, not 2.x, but 1 point. Otherwise, you will get worse. That it's not working. Therefore, I not legalize it immediately. But this guy is very careful. He said, Rainer, there's something wrong. And I said, no, cannot be. I haven't changed anything on it. And then it took me some time to find where the cause was. It's a non-trivial cause. But this happens if you have not your own code, right? Like you have this learning. It's so nice because you know at least where to look and to fix it. But here you have to really read all the release notes of Python, NumPy. I really did nothing else the whole night. Then, the precision of numbers is decided by Python itself, by NumPy, not by me, right? And arbitrarily. And then I go to tell them, but I will not be so stupid to accept this. And it's release note, 2 point something. We accept the new logic for NumPy and blah, blah, blah. And that was a big mistake. Because they got lots. I did not complain, but they got a look at. If you Google this, you find a lot of people going mad about this change. And the only reason, unfortunately, maybe there's a flag. I have to check. Have then stopped and I had the solution and said just install it the right versions. But maybe now there is a flag in NumPy or in TensorFlow to turn it on or not to counteract the critique. I'm pretty sure it will be now there. I have just to look it up again, but I was so fed up to waste the 2 nights just on Googling NumPy and TensorFlow that I stopped and then I knew what the cause was and could fix it. But that's important because, there's also a question about software. it's good that we use so many cool softwares, but if you mix and match, you have not only pros, you have some cons.
But then, so how much do you really think that this step in general, when you do it right, let's say, and how much do you really, because we spend a lot of time thinking about denoising fMRI and whatever, but I see that people spend a lot of time in creating their segmentations and making them better. So why is it the case that, what is this number one bigger limitation from a software development point of view of why the segmentations still don't look bad?
So I'm going to interrupt you here before you answer, because that's actually one of the questions that we're in the roundtable in one of. So this question, and also,
again,
and also, you're not here?
I don't know, but it's okay. I'm gonna try.
No, also because it'd be good to give like a 10 minutes break to the student before the next talk, otherwise, no.
I've got opinions. Yeah, let's talk later.
But yes, let's thank Rainer for the fantastic talk. And, yeah, let's get 10 minutes for a quick coffee. Coffee's outside.